This is the first of 3 lectures that we'll be doing that pertain to Chapter 5 in the textbook. And I'm not going to do all of Chapter 5. I'm just going to kind of do it, give you a flavor for what is called Larson's hypercube model. And it's pretty interesting, and it gives you an idea of how we can handle these things called spatially distributed queues for, say, emergency service. So if you wanted to send, if you have a bunch of ambulances on standby and you need to send one to a call, how do you dispatch the ambulance so that they are covered sometimes, if you want to use the coverage term. So section 5.1, really the first few slides here are an introduction to the definitions and exactly what's being handled in this chapter. So the definition of a spatially distributed queue is one where we have customers and the servers are spread about in a city. So it's not like, you know, when you go to an ATM machine, or, well, it's redundant, isn't it? ATM is automated teller machine. But this is where you have customers that are around the city, and then generally you're sending a unit, or they're going to be traveling to an emergency response unit. So for example, the customer might travel to a server, say an emergency room. Servers might travel to customers, which is a police responding to an incident. Same thing with an ambulance, for example, or fire, for example. The service might be on scene at the customer, and the service might be, again, at a facility. So really this one and this one are kind of the same. But the point is that they're spread out about a geographical area. Here are some of the notation, and I really just copied this from the textbook, and what I wanted to do was highlight, although I did forget to bring my highlighter, sadly, with me on my, I'm out of state right now. So let me just point out some of the types of queuing systems in a city, and they give some pretty good examples here. So we could have the server is the taxi cab, which is tabby cab, that's interesting. Taxi cab rider. We have certainly garbage collection. We've never really addressed that, as garbage collection is part of an urban system, of course. Any types of emergency vehicles. You might be interested in recreational facilities. Actually, we have customers who are the recipient of social services, which is one thing we haven't really talked about much. We pretty much talked about emergency, like police, fire, and hospital. We could have another idea is when the weather is really bad, sometimes power lines come down, right? So it could certainly be, it says vehicle repair, but we could actually have people being dispatched to certain parts of the city that have down power lines and so on. So anyways, you can read all of these if you'd like. These are the types of disciplines, and most of these are the first come, first serve discipline. So they kind of point that out. They talk about the types of queuing delay. So it's stuff that you're already familiar with because, you know, you're a human being that lives in a geographical area, but kind of puts it into perspective. So these are the things that we're going to be talking about in this in the next 3 lectures. So we'll certainly have lambda, which is going to be a system-wide arrival rate. And you're going to see that we're actually going to be dealing also with, right here, we have lambda, and then we're going to have lambda j. So we're actually going to be creating networks for service here. So lambda is going to be the system-wide arrival rate. Lambda j is going to be the arrival rate coming from a certain portion of the city. We're going to have rho, which is going to be called the utilization factor. So that's going to be the average fraction of time that my servers are busy. And that's going to be important when we're interested in equity among our servers. We'll have a capital N number of servers, so I'm kind of just circling all the things that you're going to see me talk about. We'll not be talking about new, or let's see, these are the ones I'm going to be looking at here. F, where are we here? F, we'll be talking about, yes, this here, average utilization factor for a particular server. Then the very last lecture, we'll be talking about these fraction of all answered service requests that are going to send a particular server to a part of the city. So this is these are some pretty important parameters as well. And pretty much everything else here, I'm not really going to be going into in this course. Okay, section 5.2 makes mention of something called the MG1 model. So remembering from chapter 4, so the whole reason we spent some time in chapter 4 was to get you familiar with some queuing terms. So remember, this is arrivals, services, and number of servers. So arrivals are Markovian, meaning the inter-arrival times are exponential. Service times here are general, meaning that they could really be anything, but we're not going to cover that. So in section 5.3, we're going to start out with a pretty simple example and some notation that you'll need to be familiar with. So I'm going to take a 2-unit model, and I'm going to have what's called a zero line, or zero, really you could think of this as Q, capacity. That means that when my servers are busy, any calls for service are going to be completely lost, all right? Now, I hope that this comes out, because I see that that color is quite dark. I can kind of see it. This says area A, and it has a lambda 1 here and then a 1 in a white circle, and this is area B with a lambda 2 and a 2 in a white circle. So let me explain. We're going to basically have a city that just has 2 response areas, A and B. You know, if you want, you could think of it, you know, as west side and the east side, okay? And they have different areas I'm trying to show. We have 2 response units, 1 and 2. So let me just write down here. We could think of west side, east side if you want. So just a nice simple example. We have 2 response units, 1 and 2, and if you'd like, you could think of them, if you'd like, as, I'm just going to write them as ambulance locations. So they could possibly be, you know, at a hospital. Each unit services at a rate mu. So the rate of ambulance 1 and the rate of ambulance 2 are identical. The calls for service are going to be Poisson, meaning that the number of calls is Poisson, so the inter-arrival times of calls will be exponential, just so, same thing as like an M from Markovian. And they're going to, but this time we're going to actually differentiate. So we're going to have a different call rate from area A than from area B. So as an example, let me just kind of write as an example. Perhaps lambda 1, maybe this is a larger area, maybe lambda 1 is equal to, maybe they have, I don't know, 3.2 calls for service per day, and then maybe lambda 1 or lambda 2 has, I don't know, a 1.7 calls per day. So the point is that the generation of calls is going to be different for whether on the east side or the west side. So a call from area A, when both servers are idle, is going to be dispatched or serviced by unit 1. So if I get a call in area A, I'm going to send ambulance 1. If I get a call from area B, I'm going to send ambulance 2. Now what happens if I have server 1 here, ambulance 1 is busy, and then I get another call from area A? Well, then I'm going to send unit 2. All right, so area A is unit 1's primary response area, and area B is unit 2's primary response area, but when one of them is busy, the other one will be dispatched to the call, even if it's not in its primary area. So that is how this is going to look. Now here is the state transition diagram. Now you recall from chapter 4, we had a state transition diagram where we had like state 0 and then 1 and then 2. So this is very, very similar. Ooh, let me go back here. Hang on a second. Let me go back. One thing I forgot to write down. For my calls for service here, lambda 1 and lambda 2, we're also going to have a general response or a general arrival rate, which I circled in blue on the previous slide. And this arrival rate will just be the total arrival rate for the entire region. So I wanted to point that out. So that's going to show up on this next slide right here. So here's my area. And what we're going to do this time is we're going to have a state transition diagram that is not just laid out like linearly. It is laid out kind of on 3 axes here, if you will. So, or 2 axes, I guess. So each one of these circles is going to represent the state of the system. And here's how we're going to represent the state of the system. We're going to use binary notation. So you might remember that if I use binary notation, this would be the this like the number 0, this is the number 1, this is the number 2, and so on, but it's not really a binary number, okay? So whenever we're going to have these 4 states, we'll have 0, 0, that means both servers are idle. We'll have 0, 1, which is going to mean that unit 1 is busy, unit 2 is idle. So we'll be going right to left, and it's a little bit bright right there, but I think you can see it. Then we're going to have state 1, 0. That's going to mean that unit 1 is idle, unit 2 is busy, and then finally we're going to have the state 1, 1 where both are busy. And there's no queue permitted, so we only have these 4 states. It's the simplest version. And this is the view from the textbook. So we said, and this is how we're going to be moving from one state to the next. All right, now here's how we're going to assume that we can only have one transition at a time. So I hope that you can follow this. So if we have both of my servers that are idle, the way that I go from both idle to server 1 busy, only server 1 busy, is going to be if I have a call for service from area 1. So that's why this arrow is associated with lambda 1. And let's just do all the lambdas here first. If server 1 is busy, how do I go from server 1 busy, server 2 idle to both servers busy? Well, that is going to happen if I get a call either from area A or area B. So that's why this is lambda, because it says if server 1 is busy, even if I get a call from area A, I'm still going to send server 2 because it has to be covered. So this lambda means that the aggregate arrival rate is going to be, it'll just be faster. I'm going to make that other server busy. How about if I'm 0, 0, how do I make only server 2 busy? Well, that will happen if I just get a call from server 2's primary response area, lambda 2. But if I already have server 2 busy, how do I go from server 2 busy, server 1 idle to both servers busy? Well, that's going to be a call from anywhere because I'm going to send my idle server to a call no matter where it comes from. Then you can see how we move from each of these states given a service rate. Now, in this case, if I'm going just from both servers busy to server 1 busy but server 2 idle, that just means that I'm going to be working at a rate of mu right there, because only one of them is because we're only moving from a 1 to a 0 for server 2. So that's why these aren't 2 mu, which is different from what we did in chapter 2, because now we have made our state transition diagram specific to which server is busy. So as we move from 1, 1 to 1, 0, that's just at rate mu. As we move from 1, 0 to 0, 0, that's just at rate mu, and so on. So I wanted to make sure that you understood the notation here. So my servers will be I equals 1 and 2, and we'll just indicate their status as a 0 or a 1. Okay, now the next slide is what my state transition diagram would look like for this simple model here. So I'm going to write out all of the states, and then I'll just let you know, I'll just give you the formula for each of them because that's just easier, but you could also just solve for it just like we learned how to do in chapter 4 using the matrix features of your calculator. So here I'm going to show the balance equations here for this. So let's write it down here. Balance equations. And again, it's going to be expected rate in equals expected rate out. This seems awfully bright here. I rarely say that. Okay, so let's start with state 0, 0. So my expected rate into state 0, how do I get there? Well, I can be in state 0, 1 and have a service. So we'll have mu p 0, 1. So we're using the same notation for my states, but I'm just subscripting them now with the 0, 1 or these different 4. So we can have a service from state 0, 1 or a service from state 1, 0 right here. And that is going to equal lambda 1 times 0, 0 plus lambda 2 times 0, 0. So that will just be, we could write it as lambda 1 plus lambda 2 times p 0, 0, or you could just write it as lambda p 0, 0, because remember that each one of these lambdas is just lambda 1 plus lambda 2. Right there. All right, so let's move on to state 0, 1. So the rate into state 0, 1 is I can be in state 1, 1 and have a service, or I can be in state 0, 0 right here and have an arrival, which would be lambda 1. And how do I get out of state 0, 1? Well, I'm going to have, where am I here? I'm going to have, where am I here? Lambda times 0, 1 here, and mu times 0, 1 here. So we'll have lambda plus mu, and then I'm in the state 0, 1. Let's look at state 1, 0. So in state 1, 0, how do we get into state 1, 0? Well, we can be in state 1, 1 and have a service, so similar to the previous state, or we can be in state 0, 0 and then have an arrival from area B, so that will be lambda 2. And how do we get out? Same thing, lambda plus mu, p 1, 0. And then the last state, state 1, 1, well, how do we get into state 1, 1? Well, we can be in state 1, 0 right here, and then have a call for service from either area A or area B, or we can be in state 0, 1 down here, same thing, and we just have a call from area 1 or area 2, which is this lambda 1 plus lambda 2. And then how do we get out of state 1, 1? Well, we're either going to have a service into state 1, 0 or a service into state 0, 1, and this shouldn't surprise you because it's similar to what we did in chapter 4. We're going to have mu p 1, 1 plus mu p 1, 1, which is 2 mu p 1, 1, and that's what we did in chapter 4. When we have both of our servers busy, the rate at which we can fully transition out is going to be twice my service rate, so that shouldn't be surprising. And then we also have that the sum of all of my probabilities here has to equal 1 as usual. And then for different values of mu and lambda, you could certainly set this up in your calculator and solve for these steady state probabilities p 0, 0, 0, 1, and so on. And if you did that, and if you wanted to do it using these general representations for mu, lambda, and lambda 1, what you would end up with are the following equations. So if you wanted to just plug and chug, you would get the steady state probability of both servers being idle ends up being 1 plus lambda over mu, which sometimes we call phi, plus lambda squared over 2 mu squared, and then this is really in the denominator, so it's 1 over that. And then we can have p 0, 1, and the formula for that will be, well, you take p 0, 0, and then you're going to multiply it by this term, which is a fraction, and in the numerator it will be lambda 1 plus lambda squared over 2 mu, that's the numerator, and the denominator will be lambda plus mu. And then for p 1, 0, that will be, it'll look just like this, only where you see lambda 1, you're going to see lambda 2 instead. So in the numerator we will have lambda 2 plus lambda squared over 2 mu over lambda plus mu, that term there. And then finally, the probability that both of my servers are busy will be P00 multiplied by lambda squared over 2 mu squared. So these are all values you would get, for example, as I said, if you had numerical values for lambda, lambda 1, lambda 2, and mu, or if you did it, symbolically, this is what the equations look like when you're done. And then the last slide of this lecture, it's kind of short, but I don't want to do too much too fast. We have this value, we're going to call it rho sub I, and that's going to represent the fraction of time that a particular unit is busy. Now remember, we don't have any Q here, and so the computation of rho I is really quite easy to determine. So for unit 1 here, so here we have I is, we have unit 1 and unit 2. So the fraction of time that unit 1 is busy is going to be the probability that unit 1 is busy and unit 2 is not, plus the probability that unit 1 and unit 2 are busy. And then similarly, the unit workload for server 2 will be the probability that just server 2 is busy, but also the probability that server 2 and server 1 are busy. And what you want, if you're designing, say, police precincts or where to put hospitals and such, is you want this to be equitable among the number of servers that you have. So if you had, 25 police precincts, you'd want row 1 through row 25 to be somewhat equitable, and if they're not equitable, then have some sort of a mitigation, right? I mean, we all know, we've worked with people who are, super busy and they get paid the same amount as somebody who's not busy, right? And that's not, that's not a cool working condition. Anyway, so here endeth the very first lecture from chapter 5, and we will see you in lecture 2.